Yasemin Ozkan-Aydin from the University of Notre Dame.
So, today I will talk about how biological inspired strategies help us to create a robust robots for unconventional environments. So this is a figure for most of us try our robots or run our experiments before the paper submission. And this is a clean, very precise environment where we test all the robots. But in real nature, there are a lot of challenges, like dense, uneven forests, where fallen logs, slippery leaf litters, cluttered obstacles, uneven surfaces is all of the way. And we need some robust sensing, dynamic adaptation of the gates, and interact with the obstacles other than avoid obstacles. And more challenge one, deserts. And here is again a lot of locomotion challenges because the surface is very slippery or deformable, and there are a lot of sand, dust, we can't see the environment maybe, and extreme temperature causes a lot of problems for robotic parts, and dynamic terrain and limited surface visibility. And for this one also we need advanced localization techniques and morphological adaptation like the animals use, and robust materials and sealing for our mechanical and electronics part. And even another one, there's a polar ice caps. Again, it's very extreme cold. It's minus 60 Celsius degree, and very slippery surface, and the fragile surface. And again, we need some adaptation for that too, and adaptive gates. And maybe this one, coastal wetlands, it seems kind of easy for us, but it's still a lot of muddy, waterlogged terrain, and dense vegetation, and fluctuation at the water levels. And again, it's a lot of navigation techniques, maybe multi-terrain navigation techniques we need, and we need to interact with obstacles again. So, what nature does for this case, and you can see that in the left video, it's the monkey, spider monkey is moving in dense forest. It has several appendages. It's used tail not for just for fun or for inertia, like inertia control, like Talia mentioned, but it's used for grasping and locomotion and for everything. And again, the spiders, squirrels also is very agile animals. They can move in any environment and very forest, and move on the branch to branch and move very fast. So this is one of the video one of the YouTubers took for an obstacle course, and they can do anything with 4 foot. And snakes, they don't have any appendages, but even with their soft, flexible body, they can climb or fly, some of the species, and they can do a lot of behavior. And in this video, in the snake video, you can see that depending on the diameter of the branch they trying to climb, they use a lot of different kind of strategies, not just the one single method. And in this video also, it shows that it's make a knot and try to move, even though it's a very big tube, it can climb. So we have robots, of course, for that one. This is one of the very early robot from CMU group, Dr. Chuset's group, and the robot can climb to the tree, but I'm sure this robot will do this behavior is they find a very perfect tree that fits to the joints and size of the actuators, and this behavior probably can't be done in the other tree or other size of trees. And this is another video on the right. You can see it's a jumping robot. This recently, 2 days ago in the workshop, Justin Yim presented this work. And there's this is a one-legged robot, but it has a gripper, and it can jump like squirrels, but it's still it requires the certain point to hold, not like squirrels. And in desert, there are a lot of snakes, like sidewinder snakes. It can move on this very fast, and using the different type of sidewinding gates. which is very challenging. And locomotion also in this area is also for sensing site is very important. For Sahara ants, they use there's no landmarks around, and these ants can use the sun and their clues, small clues they left while walking, and they can come to their nest very quickly using these clues, which is very challenge for the robotic systems. And in polar cap, there's penguins that can move with just maybe 2 feet, but they can also use the flippers to swimming in the snow, and they can see that it's very modular. They are not just walking; they can do other stuff too, which our robots is still just like this one is just moving with wheels. I think while we design our robots, we need to take a look at the maybe examples, not just, for example, for the locomotion, we may think about the cheetah robot is the fastest and better robot, but sometimes the small sea turtle hatchlings can be our inspiration. And because these animals are very small, but they need to survive in the very harsh environment. They need to go from nest to ocean very quickly, and they mostly do this in an environment is a sandy, muddy, is maybe obstacles, some obstacles, and maybe this kind of inspiration can make us to build better robots, maybe small, but it's more functional in the challenging environments. Like the turtle robot from our group is a small robot that has the flippers, 4 flippers, it's similar to the sea turtle hatchlings, but we try to understand in this study how this morphology and gaits and the environment interact with each other. This is embedded intelligence, we call. And with this, all the things are combined, you can create a better robots which can work on different environments. And if you push the boundaries for the biologists, the low Reynolds number is one of the environment you can't, these inertial forces are, viscous forces dominate the inertial forces. It's a very challenging environment. It's not every strategy works in there. And deep sea is very, also another one. There are animals living there. There's high pressure, limited light, dense obstacles, unknown currents, and everything. And deep underground environments is also another one. It's still, again, it's limited light. The environment is very unknown, and you need to move in this one. And of course, this outer space, which we still don't know, but there are some the temperature. There's a lot of zero gravity and some radiation. So we need to design robots that can move in that areas. For the low Reynolds numbers, maybe you never heard about that. There's the animal zoospores. They are usually there's small spores. They can live in the fungi or bacteria and move very quickly. One of the things they need to do, they need to survive. They need to go very fast and find the host and to attach the host and without consuming a lot of energy. So this makes these animals very fast in viscous on low Reynolds environments. And we inspired this one and create a robot that is on the right is swimming in a glycerin, which is very viscous environment. And this robot is compared to its size and the shape of the robot is one of the fastest one in this domain. And we also try to understand how these zoospores can inspire us to create the other robots with the soft flagella and turning behaviors, which is also another navigation techniques we will use. And we have another research ongoing on that area. And we try to understand how this stiffness of the flagella affects the locomotion. And if we go to the animal size, oops. Sorry. Oops. Okay. So if we go to the animal side, you can see that there are animals is living in that area. For example, in deep sea, if we I don't know if you know that snailfish, they can live, this is one of the video from the paper that take in the 7,500 meters in depth, and the animal still can move. This is a very, I think, challenging environment for the roboticists, to create a robot that can overcome this high pressure and also can move, navigate in the environment without any problems. And for the space, maybe you know that there's a tardigrade, there's a little guy, they can move, walk, it's a small-legged animal, and it can move or live in any condition, in space, in radiation, and high temperature, low temperature. So these are also going to be very good example to created with robust robots in the future. And where we are, so maybe you know that there are a lot of worm robots that can burrow in. The worms are very important because they can burrow in very soily environments. There are thousands, maybe hundreds of robots that can move on the smooth surface. Maybe some of them try to move under soil, but still there is no autonomous robot that can burrow under soil. So we have some limits for energy sources, some size, power limits of the actuations, and bulky control units, or mostly these are the robots if we can't non-scalable. So we need to find a way to make a robots that can maybe move like similar to animals. And what we need to do, we first identify the problem and find a good synergy between, like Talia mentioned, the biologists and roboticists, because it's very important. It should be a win-win collaboration, and you can inspire the roboticists with biology and also inspire the biologists with robots. And beyond the locomotion, we always focus on fast movement, fast locomotion, but there are more important tasks to do that. And we can also do something with biohybrid systems, like maybe sending the tardigrade with the electronic pack to the space to collect the data. This is one of the areas, I think this morning also there were some talks about that. It's very good to use the animals that is very expert in their environment and put those other things, that electronics or other stuff, to make better robots. So this is my end of my talk, and if you are interested, we have a lot of different type of bio-inspired robotic systems in our lab. Just reach out to me.
Thank you very much. Thank you. Of course, all the speakers will be around and having lunch, but if you would like to ask one question or two, you will be welcome. No, people are leaving to lunch. I have one question, though. That is, again, I'm a bit obsessed, because obviously in a large robotic system, the challenge is intelligence. But at this scale, the challenge is energy, is really the challenge. In fact, you put in the list number one, energy sources.
Yes,
Oh, there are two solutions in this. One is to have a more efficient mechanism. Or the second is to have better energy sources, batteries and so on. Could you make a short comment on that? So which directions are you pursuing in this framework project?
So energy sources, I also think that is one of the important one to make the autonomous robots. Usually we have, for example, for the burrowing robot, you have a cable coming from them. It limits all the behavior, not just the locomotion. It's pulling down, it creates external direct forces and the back. I think maybe not currently it's available, but in the future we will have a better energy sources, which may be inspired by the biological systems, gonna be collecting some harvesting energy from the environment, like maybe animals that eat in the underwater, krills, maybe create an energy source from that, or other chemicals. In the future, hopefully it's going to be more available and make the robots much, much better.
Thank you. Thank you. Okay, so I think we can close this session. I would like to thank all the speakers for fantastic presentations. Really.
Thank you.
Thank you very much.
Thanks so much.